Hello and welcome to lecture 30 of our Essentials of Semiconductor Device Physics course. Okay, so last time we concluded our analysis of p-n junctions in equilibrium, and this time we're going to begin our analysis of p-n junctions out of equilibrium by introducing the concept of quasi-Fermi levels. Now, to understand the notion of quasi-Fermi levels, we need to consider systems out of thermodynamic equilibrium, and we could in principle consider any system we want. I find it easier to use as an example an intrinsic semiconductor that was taken out of equilibrium by shining light into it. So when we shine light into a semiconductor, and if the energy of the photons is higher than the band gap energy, then the photons can be absorbed by the semiconductor, and when a photon is absorbed, then it transfers its energy to an electron that was in the valence band, so the electron is excited to the conduction band. So absorption of a photon creates an electron-hole pair, and the system is out of equilibrium because there is a new form of energy. In this example, electromagnetic energy that is being pumped into the system. And the important feature to notice here is that the concentration of free electrons and the concentration of holes changed when we took the system out of thermodynamic equilibrium. Now I need to say a few words about systems in quasi-equilibrium. So to understand what is meant by quasi-equilibrium, suppose that we don't have the pump. So suppose we consider an intrinsic semiconductor in equilibrium. So ignore the photons for now. We already know that there will be a concentration of free electrons, a concentration of holes. We already know how to calculate them. But even in equilibrium, there is a constant generation of free electron-hole pairs due to thermal excitation of electrons from the valence to the conduction band. But the concentrations do not change in time because this process, the generation, is compensated by the opposite process, which is recombination. So recombination describes the process whereby a free electron comes back from the conduction to the valence band, filling a hole, and thus destroying an electron-hole pair. The charges do not disappear, but the electron is no longer free, and there is no hole anymore. So we lose an electron-hole pair with the process of recombination. So in equilibrium, we have a constant generation which is compensated by the recombination of free electrons and holes, and the concentrations do not change in time because the rate of generation is equal to the rate of recombination. And now suppose we pump the system, so we take it out of equilibrium again. But let's suppose that the pump power is constant in time. So the rate of energy input is constant in time. If the pump is constant, we're going to reach a stationary state where the concentrations will no longer change in time. These concentrations of free electrons and holes, they will be different from the concentrations in equilibrium because the system is not in equilibrium. But they share this important feature of systems in equilibrium that the concentrations do not change in time. So in this situation, we say that the system is in almost equilibrium. And instead of saying almost, we use the word quasi. So the system is in quasi-equilibrium. When it is not in equilibrium, the concentrations are not the concentrations in equilibrium, we have an external pump source, but the concentrations do not change in time because the pump is constant in time. And we actually can extend this notion to systems that change slowly in time, even though we cannot define in our course what is actually meant by slowly. This is a bit out of our scope. So from now on, every time we speak of a system out of equilibrium, we're going to assume that the system is in quasi-equilibrium, in the sense that we have just discussed. Okay, so let's suppose then we have constant illumination, and then we created these new free electrons, which means that the concentration of free electrons increased. And we learned that if the concentration of free electrons increase, that means that the Fermi level goes up. So that's why I'm representing the Fermi level here as being in a higher level than in the intrinsic semiconductor. But each new free electron in the conduction band left behind a hole. These electrons came from excitation of electron-hole pairs. So if we are increasing the concentration of electrons, we are necessarily, in this case, also increasing the concentration of holes. And we've learned that if the concentration of holes increase, then the Fermi level needs to move down. So compare this situation, the situation where we took the system out of equilibrium by shining light into it, with the situation where we change the concentrations by doping. When we do n-doping, we increase the concentration of free electrons at the expense of the concentration of holes. The concentration of holes reduces. In p-doping, we do the other way around. But here, we are increasing at the same time both the concentration of free electrons and the concentration of holes. That means that the Fermi level needs to go up and also needs to go down. In other words, the Fermi level is split into two new Fermi levels. One Fermi level for electrons, which we call quasi-Fermi level for electrons, and one Fermi level for holes, which we call quasi-Fermi level for holes. So the splitting of the Fermi level into quasi-Fermi levels is the signature of a system out of equilibrium. And this happens every time we take the system out of equilibrium. It does not matter how we took it out of equilibrium. So in the next lecture, we're going to see that when we connect the p-n junction to a circuit, we are also taking it out of equilibrium, so the Fermi level will be split into quasi-Fermi levels. And we can still use the equations that we derived in previous lectures, as long as we use the correct Fermi level. Now, instead of using the Fermi level, we use the quasi-Fermi level for electrons when we are using the equation giving the concentration of free electrons, and we use the quasi-Fermi level for holes when we're using the equation for holes. So notice that the quasi-Fermi Fermi level for electrons is close to the conduction band. This is why this concentration is high in this situation. And notice that the quasi-Fermi level for holes is close to the valence band. This is why the concentration of holes is also high. So we can still keep these equations as long as we use the quasi-Fermi levels. And we can also interpret them as also applying to the system in equilibrium, but this is a particular case where all quasi-Fermi levels coincide with each other, so we call them a Fermi level. And recall that we have two versions for these equations. This is the equation in terms of the concentration of free electrons in an intrinsic semiconductor. This is the parameter assuming that the intrinsic semiconductor is in thermodynamic equilibrium. So we can still use this equation as long as we plug the quasi-Fermi level for electrons here and the quasi-Fermi level for holes here. So in the next lecture, we're going to use these concepts to begin our analysis of p-n junctions out of equilibrium, and of course our main interest is to study what happens to the p-n junction when it is taken out of equilibrium by connecting it to a circuit. And that's what we're going to analyze in the next lecture. And as always, we're going to begin with a qualitative analysis. So see you next time.